thanks for watching, and today I want to show you how to use multivariable calculus to easily find the area of an ellipse. And I think today's video really illustrates how nice parametric equations are. Because sure, you could express an ellipse with Cartesian coordinates, but here it's nicer, to illustrate this and to calculate the area. So first, let's draw a picture of this. So what is x and y? So this is really cool. When I say x is 3 cosine of t, it sort of tells you that the width of the ellipse goes from -3 to 3. And when I say y is 2 sine of t, it means the height goes from -2 to 2. So all you need to do is draw an ellipse with width 3 and height 2, which becomes something like that. So this is the ellipse we're talking about. Okay. Alright, however, it doesn't quite tell you how to evaluate this. And to evaluate this, let me motivate something again from calculus. So suppose you have two functions, f and g, and you want to calculate the area between the two curves from A to B. Question is, how do you find this area? Well, what you would do is just to calculate the integral from A to B of f of x minus g of x dx, which here becomes really the area from A to B of the bigger function minus the smaller function. So this is big and this is small. And it turns out to calculate the area of this ellipse, we do the exact same thing. Let's keep the picture and the equations and deal with the smaller ones. Well, I do need a bigger whiteboard, but it's the only one that's provided to me, so it's okay. Alright, so here it's still true. The area is the integral from A to B, which here is from -3 to 3, of the bigger function minus the smaller function dx. And now let's use a little bit of symmetry. Suppose here we have x and this is y. So suppose the big function is y. By symmetry, the smaller function has to be minus y. Because notice, this portion of the ellipse is the same as the top portion, but just reflected across the x-axis. So, because big is y and small is minus y, the area becomes integral from -3 to 3 of y minus y dx. And this just becomes 2y, and then this becomes 2 times integral of -3 to 3 y dx. This is all in good, except the problem is y is not a function of x, it's a function of t. But this is not a problem at all, actually, because it turns out there's a neat little trick to go from Cartesian to parametric coordinates. Namely, take this dx and multiply top and bottom by dt. And then what we have is 2 times the integral from something to something. So that's a point I'll express soon. Okay? Y, in this case, remember, is a function of t, y of t. dx over dt, that's the same thing as saying x prime of t, dt. So this is indeed our area in terms of an integral. So I guess let me erase this. So again, what we found is that the area is 2 times integral integral from something to something of y of t, x prime of t dt. Okay, now let's use our y. So it's 2 times integral from something to something of 2 sine of t. X prime becomes minus 3 sine of t dt. And so in the end, we're left with minus 12 integral from something to something of sine squared of t dt. The question is, what are those question marks? So literally, that's the question. And remember that here we're dealing with t. So in the end, to find those question marks, we need to find some times. And so, what we really have to ask ourselves, because our previous integral was from minus 3 to 3, we have to ask ourselves, what t corresponds to minus 3 and what t corresponds to 3? And for this, all we have to solve are the equations for x. And by that way, totally fine to set y equals to 0, but turns out here it's slightly more correct, I guess, to set x equals to 3. So, first of all, let's do minus 3, I guess. So x of t equals to minus 3. That means 3 cosine of t, it's minus 3. So cosine of t is minus 1. And because t was from 0 to 2 pi, t is actually equal to pi. So the important thing is this t here corresponds to pi. And so in particular, make sure to respect the order of integration. Because the lower thing corresponded to minus 3, the lower thing here has to be pi. It's just like integration and substitution, where you also respect the order. You do like u of a and u of b. Do not change it. Okay, that's for the first thing, and now let's do it with 3. X of t equals to 3. That means 3 cosine of t is 3. So cosine of t is 1. So t equals to 0. And so the right point corresponds to t equals to 0. And so the upper integral becomes 0. And that's why I think it's better to do this minus 3 and 3 business instead of y equals to 0. But that's wonderful, because now we actually have our integral, and we can finally erase the picture. So our answer then becomes minus 12 integral from pi to 0. Let's just reverse this. So 12 times integral from 0 to pi sine squared of t dt. Alright, either you know it or you don't, but I will make a video on this if you want. But all you do to calculate this integral, use sine squared of t is 1 minus cosine of 2t over 2. And in the end, what you get is that this is 12 times pi over 2. And that becomes 6 pi. And so it's really cool. We didn't use like a little bit of trig substitution, so implicitly. But the next question is, great, we found 6 pi. How does that relate to our data? Well, remember, x was, keep forgetting, x was 3 cosine of t, so it's 3 times 2 pi, where x was 3 cosine of t, and y was 2 sine of t. And in particular, the cool thing is, if this were a and this were b, then the area of the ellipse would be pi times AB. And more interestingly, if it was actually a circle, we had r and r here, then it would be pi r squared, which is exactly what we expect. Alright, I hope you like this little parametric equation excursion. If you want to see more calculus and more multivariable calculus, or just math in general, please make sure to subscribe to my channel. Thank you very much.